welcome to this video overview of graphing a rational function by hand without a calculator. Specifically, a rational function that will end up having an open dot. The function that we are going to graph is written on the screen, and the first thing that we will need to do is factor both the numerator and the denominator of our rational function. So we'll just take a few seconds here and factor the numerator. We'll have to have a 2x and an x leading off each factor. Things that multiply to be 20. What if we went here with a 5? That would give us a 5x, and a 4, that would give us an 8x. We would want a minus 8x plus 5x. That should work up top. Then it's just a difference of squares down in the denominator. So it should be a 2x plus 5 times a 2x minus 5. Oh, and look at that. We have a common factor on both the top and the bottom of our rational function, the 2x plus 5. That's a giveaway to watch out for an open dot, and we're going to simplify this, x plus 4 over 2x minus 5, provided that x is not equal to a negative 5 halves, which is the zero of the common factor. So now let's write some things out. We need our x-intercepts. Use the simplified rational function because the negative 5 halves is really a phony. It's a fake. It divides out. So the x-intercept where it crosses is going to be at x equals 4, where we get y equals 0. The y-intercept, and again you can just simply go to the simplified form, plug in x equals 0, those disappear, and it's going to be a positive 4/5 for the y-intercept. Domain. There are two values that are not in the domain. Specifically, we have negative 5 halves and positive 5 halves. So we could say x is not equal to plus or minus 5 halves. If I ask you to write that out in interval notation, please make sure that you're capable of doing so. Now the thing is, we have an open dot at one of those places. It would be when x was equal to a negative 5 halves. Now, how can we determine the corresponding y value for when x is negative 5 halves? Well, we plug in negative 5 halves to our simplified function. And yes, it might not be the nicest looking thing in this problem, but we can simplify it reasonably. Negative 5 halves minus 4 all over 2 times a negative 5 halves minus 5. Up in the numerator, that's going to be a negative 13 halves. In our denominator, it looks like we have a negative 10. Negative 5 minus 5 should be a negative 10. And simplifying accordingly, this should be a positive 13/20 for the y-coordinate of our open dot. Now that we've taken care of the open dot, we have to turn our attention to the other problem spot in the domain, which is the fact that we have a vertical asymptote at x equals positive 5 halves. So we will write out our vertical asymptote behavior. The limit as x approaches 5 halves from the left of our function r of x, and the limit as x approaches 5 halves from the right of our function r of x. Watch the notation being used for limits. I will be picky about that. So go to your simplified form. If we're plugging in a number close to 5 halves, the numerator is going to be negative. In this case, the denominator is going to be, we're plugging in 5 halves, it's going to be 0. If we're plugging in a number slightly less than 5 halves, this is going to be slightly less than 5. And a number slightly less than 5, like 4.9, minus 5 is going to be negative as well. When we simplify, two negatives will make a positive, and when you divide by 0, you get a positive infinity. On the other hand, numerator should stay the same. It's going to be a negative number when we plug in a number slightly larger than 5 halves. But now the denominator, when we plug in a number close to 5 halves, we get close to 0. But as long as that number is larger than 5 halves, that 0 is always going to be larger than 0. So a negative divided by a positive will be a negative, and that turns out to be an infinity as well. There's our vertical asymptote behavior that we'll have to be mindful of when we draw the graph. Other item that we have to consider, what happens for the end behavior? So when we look at the end behavior on this one, r of x, as I plug in a number really large, the largest power of x in the numerator is x. The largest power of x in the denominator is just our 2x. When we simplify that, it's going to be close to 1/2. So this is going to have a horizontal asymptote of y equals positive 1/2, meaning that as x gets close to negative infinity, our function gets close to 1/2. And the limit as x approaches positive infinity of our function is likewise going to be 1/2. So let's put all this stuff onto a graph. Oh, there's one thing that we haven't yet done. Let's back up for just a second. When we do the end behavior, we also want to look to see if it crosses the horizontal asymptote. Well, if that's the case, we would have that y value of 1/2 has to equal our simplified function of x minus 4 all over 2x minus 5. Cross multiply here to solve, we'll get 2x minus 5 is equal to 2 times the quantity x minus 4, which is really 2x minus 8. Is negative 5 equal to negative 8? Not the last time I checked. So it doesn't. The graph doesn't cross its horizontal asymptote. So let's sketch our graph here. When we get a sense of where we're at, we have 5/2, negative 5/2, 4. Each of those things are going to be key points that we want on the graph. It's going to be kind of symmetric. Maybe leave a little bit more room on the right as we draw this one though. Here's our graph. Make sure we label the axes because that's going to help me distinguish the axis from a vertical or horizontal asymptote. And in this problem, remember we had our vertical asymptote at positive 5/2. So here comes our vertical asymptote at positive 5/2. And let's label that accordingly. This is x equals 5/2. We had an open dot at negative 5/2, comma 13/20. So over here, somewhere like this, we'll have an open dot at negative 5/2, comma 13/20. That's an odd point, although the denominator on the x-coordinate evens it out a little bit. Now what else do we have? An x-intercept at 0, 4/5. 0, 4/5 I think will be somewhere like this. Always get a sense of where fractions fall. 4/5 would be larger than 13/20. Please graph it appropriately. X-intercept is at 4, 0, so that'll be over here. We'll put the point 4, 0. For the vertical asymptote behavior, as we got really close to negative 5/2 from the left, or to positive 5/2 from the left, it went to positive infinity. From the right, it went to negative infinity. So left, we go to positive infinity. Right, we go to negative infinity. And we had a horizontal asymptote at y equals 1/2. 1/2 is less than 13/20, so it's probably going to be in here somewhere that we have our horizontal asymptote of y equals 1/2. Again, things don't have to be drawn perfectly to scale, but they have to fit in the proper locations on the graph. Doesn't cross either asymptote, so now we connect our dots. And over here on the left, it's going to do something like this. Make sure it gets close to but doesn't cross our horizontal asymptote. And over here on the right, it's going to come up, go through the x-intercept, and get really close to the horizontal asymptote. That would be the graph that satisfies all the conditions we had. We've labeled our open dot, our y-intercept, our x-intercept, the vertical asymptote, and the horizontal asymptote. That would be sufficient to graph this rational function by hand.